welcome to another episode of Twiml Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. This week, we continue our series on industrial applications of machine learning and AI with a conversation with Chelsea Finn, a PhD student at UC Berkeley. Chelsea's research is focused on machine learning for robotic perception and control. Despite being early in her career, Chelsea is an accomplished researcher with more than 14 published papers in the past 2 years on subjects like Deep Visual Foresight, Model-Agnostic meta-learning, Visuomotor learning, just to name a few. And we talk about all of these in the show, along with topics like zero-shot, one-shot, and few-shot learning. I'd also like to give a shout out to Shreyas, a listener who wrote in to request that we interview a current PhD student about their journey and experiences. Chelsea and I spent some time at the end of the interview talking about this, and she has some great advice for current and prospective PhD students, but also for independent learners in the field. Also, during this part of the discussion, I wonder out loud if any listeners would be interested in forming a virtual paper reading club of some sort. I'm not sure yet exactly what this would look like, but please drop a comment in the show notes if you're interested. Okay, once again, I'm going to deploy the nerd alert for this episode. Chelsea and I really dig deep into her research, and this conversation gets pretty technical at times, to the point that I had a hard time keeping up myself. Thanks again to our sponsor for this series and my industrial AI research, Bonsai. Bonsai offers an AI platform that empowers enterprises to build and deploy intelligent systems. If you're trying to build AI-powered applications focused on optimizing and controlling the systems in your enterprise, you should take a look at what they're up to. They've got a unique approach to building AI models that lets you use high-level code to model the real-world concepts in your application, automatically generate, train, and evaluate low-level models for your project using technologies like reinforcement learning, and easily integrate those models into your applications and systems using APIs. You can check them out at bons.ai, bons.ai, and definitely let them know you appreciate their support of the podcast. And now, on to the show. All right, hey everyone, I've got Chelsea Finn on the line with me. I'm super excited to have Chelsea here to speak with us. Chelsea is a PhD student at UC Berkeley, and she is co-advised by both Peter Abil and Sergey Levine. By the time this podcast is posted, you'll have heard my interview with Peter, and we'll be digging in a little bit deeper into some of the things we spoke about with Peter with regards to reinforcement learning. But in particular, we'll focus on Chelsea's research into topics like deep sensory motor learning and few-shot learning and some other things she's working on. So Chelsea, thanks so much for joining us.
Thanks for having me.
It's great to have you. Why don't we get started by having you tell us a little bit about how you got interested in AI and how you got to where you are?
Great. So I did my undergraduate at MIT as an undergrad, and I pretty early on decided that I wanted to major in computer science. And once I made that decision, there's a lot of different things that you can do with computer science, but machine learning and AI was the thing that I found myself most interested in, given how much math it has. Unlike some other areas of computer science, there's a lot of math involved, probability, statistics, and I like that grounding in math. Mm-hmm. And I also find that AI has a lot of very important applications and I think has the potential to have a big impact on society.
Mm-hmm. Absolutely. And I think the further we get with AI, the more of these potential applications we're seeing, in particular, some of these industrial use cases, where we're using AI to control robotics and help automate things. And that is a big focus of your research, is it not?
Absolutely. I work a lot with real hardware and trying to get robots to learn how to do tasks and act intelligently, ultimately.
So why don't we talk a little bit about some of the challenges that are involved in doing that?
So unlike many problems in machine learning, In robotics, you have a physical system that is in the real world and collecting data, and the actions that you take affect the environment and affect the world, and then affect what actions you want to take next. So you can't just download some data set and process it in a passive way. You need to actually be collecting data online and then learning from that data and then repeating, essentially.
And when you're collecting that data online, like that, that poses a big challenge, particularly if you're working with systems that aren't in a lab environment, but in some production use. Can you talk a little bit about some of the specific challenges with regard to data collection? And are there, techniques, or is there research being done that's focused on that particular slice, how to make that data collection more effective and efficient?
So some of the big success stories in robotics, in industrial applications, has largely been in factories and in very controlled settings where you can essentially just pre-program exactly what motion the robot is going to be doing ahead of time, and then just have the robot repeat that action again and again.
Mm-hmm.
In these industrial applications, you really don't see robots even using any type of perception. They're simply just blindly executing motions. In machine learning research for robotics, we're trying to move beyond that. And I think that what learning will bring to robotics is the ability to adapt to new environments and learn to do tasks in very unstructured environments where you don't know what the world looks like ahead of time, and the environment might be dynamic. A lot of research right now in robotic learning is still in lab environments because that's where we can set up controlled experiments. It's more convenient to collect data in your lab than actually putting the robot out into the real world. But I think that in the very near future, we're going to start seeing more and more research where robots are actually out in the real world and collecting data, because that's where we'll be able to get the diversity of data that we need to be able to effectively generalize to new tasks, to new types of objects, etc.
One of the things that I've seen that's been really interesting has been the use of, clusters, if you will, of robots that are operating in parallel to try to accelerate, both data acquisition and learning. Are you doing anything with that kind of environment?
Yeah, so I did an internship at Google Brain about a year ago now, where I worked on 10 robot arms that were all the same and could collect data in parallel and share their experiences so that they could more efficiently collect a very large amount of data. And with that, we were able to basically give a bunch of objects to each of the robots and let them play around with those objects and share their experience with one set of objects with another robot who had an experience with a different set of objects. We also now have 4 robot arms here at Berkeley, and we might get more that we're just getting that set up right now, and we're soon going to be able to have the capability to set something up at Berkeley in a similar fashion to what we did at Google.
Oh, that's great. Is there a name for that use case of the robotics where you're training them in parallel and you're, in the middle of the training, transferring knowledge between the different robots? It sounds like, some version of like active transfer learning or something like that. Is there a standard name for that yet?
No, not yet. We typically just call it large-scale robotic learning.
Okay. Well, let's maybe take a step back. When I saw your talk at the Rework Deep Learning Summit, you started with a particular example that you used in your research and kind of built your discussion of the various challenges and the research you were doing around this example. And if I remember correctly, it was something along the lines of taking, triangular blocks and putting them in the right holes or something like that. Can you maybe, walk us through that scenario and then talk us through, some of what you discussed in your presentation?
Yeah. So the first thing that I set out to do in my PhD was to try to see if it was possible to learn a deep neural network that maps from what the robot sees to the actions that the robot takes, and see if we were able to learn a policy that does this for manipulation skills. And we were able to do that successfully. And one of the first tasks that we experimented with was inserting a block into a shape sorting cube. And I guess usually when I begin with that example in my presentations, I talk about, for a human, this is very intuitive. to do, because over the course of your life, you've learned how to guide your arm such that the block falls into the hole nicely. But for a computer, for a robot, what the robot sees is just a bunch of numbers, a huge array of numbers in the picture. And likewise, the actions that it's taking, maybe the torques applied to the joints of the arm, is also just a bunch of numbers. Mm-hmm. And to be able to map from one set of numbers to another set of numbers, to do that accurately and to do that in a way that will robustly handle a variety of environments, there's no way that a hand-engineered approach will work. We need to be able to learn that function, and we need things like deep neural networks to provide a very flexible function in order to be able to effectively do learning in that scenario.
Yeah, I think that's a great way for folks to think about what deep learning is. Thinking about it as a function that maps from one set of from a set of inputs to a set of outputs. It's interesting that that we're able to throw all this data at the problem and have the computer figure out these functions.
Yeah, absolutely. And actually, one of the challenges in robotics is that typically in deep learning, you gather a very large data set and then train your neural network on that data set. Whereas in robotics, it's impractical to collect a huge amount of data for a task that you might want to train, because you're actually collecting that data on a real physical system.
Mm-hmm. And so are there techniques that can be used to, or let's maybe talk a little bit about the techniques that can be used to address that problem? Deep learning historically requires lots and lots of data. In these industrial environments, it's difficult to collect lots and lots of data. What can we do then? Yeah,
so there's been a number of approaches. One is to, as we talked about before, just get a bunch of robots and have them collect data in parallel. Well, actually, one of the challenges with that approach is that if you're having a lot of robots collect data, you don't want to have a human for every single robot labeling the data or resetting the environment or providing other means of supervision, because that defeats the point of having the robot there in the first place. So you can get a lot of data, but you need an algorithm that can learn from the raw data rather than from labeled data, like we see in some of the most successful applications of deep learning. Another approach to this problem is to train in simulation, where it's practical to acquire a lot of data and then try to use what you learned in simulation to be able to effectively act in the real world, either with zero-shot transfer, where you get zero data in the real world, or few-shot transfer, or just fine-tuning in the real world, where you just need less data in the real world than you would need otherwise if you didn't have that simulated data.
Well, maybe let's talk a little bit about those three things. So with simulation, maybe walk through the process of using a simulator to train a deep neural net.
Yeah, so in simulation, we can use algorithms that require a lot of data, specifically reinforcement learning algorithms. Reinforcement learning algorithms are typically very data inefficient because they don't have the exact input-output labels that you have in supervised learning. You're not just trying to map from one thing to another where you would know exactly what the output should be. Instead, you get experience in the environment, and then you get feedback from the environment on how well you did. And that feedback might be delayed, it might be sparse, so you might not get it very often, or it might not be very detailed. And so as a result, reinforcement learning algorithms are significantly slower and require significantly more data than supervised learning problems. And we already know that supervised learning problems require a lot of data. So typically what an approach like this might look like is train a policy in simulation using your favorite reinforcement learning method, and then take that policy and try to transfer it into the real world, either just by running it in the real world and hoping that it works, potentially with some modularity to like a vision system on the robot, like that's specific to the robot versus specific to the simulation, or a controller that's specific to the robot and specific to the simulation, or trying to initialize with that policy and then fine-tune in the real world. One of the reasons why that transfer doesn't just happen automatically is that one, simulated vision is usually lower fidelity and not as realistic as the vision that we get from cameras in the real world. And physics simulation, the physics in simulators is actually not at all accurate, especially when you encounter a contact between two different objects. Modeling contacts and exactly what goes on within that contact is quite complex, so it's not something that we can accurately model in simulators.
Mm. So that's really interesting. So the specific challenge there is, for example, in simulation, you're modeling a robot manipulator like a hand that's picking up a block. I can imagine that the physics governing how that simulator is grasping that block and, the coefficients of static friction and dynamic friction and all the things that determine the way the block will ultimately sit in the gripper can be quite difficult to model. Is that basically what you're describing in terms of when you're modeling two bodies?
Yeah, exactly.
And so with the difficulty in modeling that, how do you account for that? Do you just do a rough approximation and assume that the difference is noise in the system that your model just needs to account for, or are there specific techniques for dealing with that?
Yeah, simulators have various ways to approximate them. Then, yeah, generally the learning algorithm doesn't look any different in simulation versus in the real world.
Okay. One conversation that I had that I think I mentioned in the conversation with Peter as well was a conversation with Stefano Ehrman over at Stanford, who was talking about like incorporating physics into models. And Peter and I talked about that, I think fairly generally. Is that something that comes into play specifically in your work and in this, this issue of the grippers, for example, or the contact between the robot and other objects?
So you're asking, like, do we try to learn models of the world?
I guess I'm asking, how do you try to incorporate pre-existing knowledge about the way grippers grip and, objects respond to being gripped into your deep learning models?
So some of our algorithms, we do incorporate knowledge about the physical world. For example, we have a certain type of model. Usually in one of the algorithms that we use and that we can run on real robots, we use a Gaussian mixture model as a prior on a learned time-varying linear model. It is getting a bit complicated, or a bit technical, but generally a Gaussian mixture model is, or at least a prior from a Gaussian mixture model is a fairly reasonable way to model physics, in that oftentimes there are different modes of physics. There's whether you're in different types of contact, whether you're in free space, and that sort of model is well suited for that.
Actually, I'd love to have you walk us through the details on that. What can we start with? What is a Gaussian mixture model?
Yeah, so this is one small part of a much larger algorithm for learning policies on the real robot.
Mm-hmm.
So a Gaussian mixture model is a distribution where there are multiple mixture components, and each mixture component is a Gaussian distribution, so a normal distribution. And then each component also has a weight. And then the Gaussian mixture model is simply the weighted sum of all of the Gaussians.
And is the Gaussian mixture model, are you using a mixture to model one specific thing, or are you using that mixture to model several phenomena at once?
We're using the mixture to model a mode of dynamics, where by dynamics I mean a conditional distribution of the next state given the current state in action. So you're basically trying to predict what the next state is going to be given where you are right now and the action that you take. And that conditional distribution will depend on whether or not you're in contact, whether or not your finger is sliding across the table versus in static contact, or versus whether or not you're in free space. And so we're using each component of the Gaussian mixture model to model those different modes of your dynamics.
Mm-hmm. And so you mentioned a few things in terms of your, finger sliding and those things. Do each of those map one-to-one to a component of the mixture, or is all of that modeled by the whole of the mixture?
Each of those will typically map to one component, although usually you don't know the number of components a priori, so you set it to a number that you think is slightly larger than the actual number of components, just like in k-means or in clustering algorithms.
Okay. All right. So you've got this mixture that models, some of the physics that rolls up into the broader model that you're trying to build. And you said you use that as a prior for
fitting a model.
Okay. And so when you say you're using that as a prior, you're basically using the output of that Gaussian mixture model as an input to your deep neural net. Is that the right way to think about it?
So in this case, actually, the dynamics model that we're learning is not a neural network. We're learning a local time-varying linear model, where by time-varying linear, I mean that you basically sample a bunch of trajectories on your robot, and then at every time step in those set of trajectories, you fit a linear model using linear regression. And then the Gaussian mixture model is fit to all of the time steps of all of the samples, and that's used as a prior for linear regression, done at every time step.
Okay, got it.
And then ultimately we use this, well, there's more steps involved, but you use this dynamics model that you fit to acquire an optimal policy for a certain version of your problem.
Okay.
And then when you have an optimal policy, you can, at a high level, kind of the top-down explanation is that given a certain manipulation problem, you can decompose your problem into different instances of the problem, like for a single start position and a single end position. And then we are solving for the optimal policy for each individual condition using optimal control and using this linear model that we fit.
Mm-hmm.
And then once we solve each of the individual problems, then we use that for supervised learning of a deep neural network that can solve all of the instances of the problem.
Okay, so let me try to paraphrase that to make sure I'm following. So you've got, it sounds like we are talking here, you mentioned point A and point B. Are we talking about, strictly the problem of you've got a, robot arm, let's say with, n degrees of freedom, and you're trying to figure out a path, to translate, to get the gripper from point A to point B using those motors? Is that the scope of the problem that we're talking about, or have I read into that too narrowly?
That is a little bit too narrow. So it's not just moving the gripper of the robot. It could also involve moving objects. It could be, so this algorithm has also been applied to manipulating objects within a 5-fingered hand. A slightly different version of the algorithm has also been used for locomotion, robot locomotion.
Okay. So then maybe taking a step back, it sounds like you've got something that's, you're trying to figure out how to get it from point A to point B, and you've got some, underlying dynamics that you need to model. And so you train a linear model to tell you basically how to move your motors to get the thing from point A to point B, or state A to state B. And then once you have those linear models, you're able to use them to generate more data that you can train deep networks with. It's basically you're training a data generator.
Essentially, yeah. So the data generator is that in any given kind of robot manipulation problem, you can see your current observation, but you don't know what action you should take. And what you want to figure out is what action to take. And so the data generator is figuring out what action you should take for any given observation. And then once you have the actions that you should take, you can then just apply plain supervised learning with your neural network.
Maybe let's take a step back to kind of the broader problem, which is the putting the blocks in the right places. A big part of your research is the relationship between the robot is seeing that problem from a computer vision perspective. And you're essentially, the intelligence that the robot is acting on is kind of largely driven by, the manipulation of, or an observation of, the pixels coming from a camera or set of cameras. Can you talk a little bit about the, broadly speaking, the relationship between, computer vision and the work that you're doing in robotics? And then, maybe we can drill into some of the specifics.
Yeah. So a lot of the algorithms that we develop for robotics, we aren't necessarily specific to certain sensory modalities like tactile or vision. We want them to work with a fairly wide variety of modalities. Vision is perhaps one of the most interesting because it gives you a lot of information about the environment, and it also is one of the most challenging because it is very high dimensional and not high dimensional in a way that's readily interpretable by a lot of these algorithms. Mm-hmm. One of the other reasons why we use vision a lot is because tactile sensing, while can give you a lot of information, good tactile sensors are hard to acquire. And they're typically either very expensive or very fragile and break a lot. So a lot of the algorithms that we develop, we try to incorporate, we use convolutional neural networks if we're going to use vision. Convolutional neural networks are very efficient and very effective at doing their job, at basically localizing objects or inferring things about the environment, etc. So a lot of my work will be developing algorithms based off of reinforcement learning, imitation learning, or inverse reinforcement learning, but focusing on algorithms which can scale to high-dimensional inputs like vision.
Okay. You mentioned inverse reinforcement learning. What's that?
Yeah, so reinforcement learning first is the problem of given a reward function and the ability to sample experience from your environment, figure out what the optimal policy is for that reward function, figure out what actions you should take given a current observation. Inverse reinforcement learning is essentially the inverse of that. So in inverse reinforcement learning, you assume that you have rollouts or basically trajectories from the optimal policy from an expert like a human, and your goal is to figure out what the reward function is. So your goal is to figure out what the human was trying to accomplish. And then ultimately, once you've figured out what the human was trying to accomplish, then you also want to learn a policy for yourself that also accomplishes what the human was trying to accomplish.
Mm-hmm. So is an application area of that when you're doing imitation learning and you have a human explicitly move a robot from, one position to another, you can then use inverse reinforcement learning to learn a policy that would produce that same motion?
Yeah, exactly. So the typical application is given a set of demonstrations from a human, try to figure out what the human was doing, and then figure out how to do it yourself.
Mm-hmm. And then you said in your previous description, you said not just what the human was doing, but you kind of characterize it as why the human was doing that, or at least that's what I read into the way you said it, like the human's intent. Is that, do you make that distinction between what the human was doing and, the model, learning some degree of intent or higher level purpose, or am I reading too much into it?
No, that's absolutely right. So the reason why this is interesting is that if a human is doing something, you don't want to necessarily mimic the exact actions that they do because you might have a different arm that looks slightly differently, or maybe the way that they're doing it isn't quite optimal, or you want to be able to generalize what they were doing to new scenarios. And in those new scenarios, you don't want to do exactly what they did. You want to achieve what they were trying to achieve. And so inverse reinforcement learning, you're adding structure to the problem of imitation learning, where you're assuming that they were acting according to some reward function, and you're trying to infer what that was and what they were trying to achieve.
Mm-hmm. And so bring all this back to the problem of the placing the blocks for us.
Okay, so in the block scenario, you'd see an example of a human putting the block in the shape sorting cube, and then you would try to infer the fact that their goal was to get it inside the cube, not just to take the actions that they were taking. And then once you infer that, figure out a policy for doing that. The block example perhaps isn't the best example for inverse reinforcement learning because providing a reward function for that task is fairly straightforward. Your goal is to physically get this red block into the shape sorting cube. But in many other scenarios, it's actually hard to write down what the reward function should be. And that's actually one of the big challenges in applying reinforcement learning to real-world scenarios. So for example, say you want your robot to pour a cup of water from one cup to another cup. In that task, you want all of the water to end up in the target cup. You don't want any water to spill. You probably want the robot to be somewhat gentle. And encoding those things in a reward function requires a lot of engineering. Like you might need actually like a liquid detector to be able to detect where the liquid is and to detect if something got wet. And then also characterizing whether or not the robot was gentle.
Mm-hmm.
And so engineering that reward function may even be more work than engineering the behavior itself. And it's much easier just to show the robot, this is the task that I want you to do.
Mm-hmm. But you still need to, do you still need to give the robot examples of a failure or of failures? Like, to what degree does that come into play as well with supervised learning? So you've got, examples of, hey, I'm successfully getting the cup of water from point A to point B, and you can label those as successes. But what about labeling, this is a failure explicitly, even though 80% of the water may have gotten from point A to point B? Does that make any sense?
Yeah. So typically in inverse reinforcement learning, you only give successful demonstrations, although thinking about how you could incorporate failed examples is an interesting research direction. Not a lot of research has been done there. And actually, perhaps an interesting analogy for people is that for people that are familiar with generative adversarial networks, you can actually show that the inverse reinforcement learning objective, that is one of the ones that's most widely used, is mathematically equivalent to the objective of a discriminator in a generative adversarial network. So in generative adversarial networks, you're given a data set of images, and the goal is to be able to generate images from that data set, or that look like images from that data set. And the goal of the discriminator in a generative adversarial network is to figure out if an image was generated and is fake, or if the image came from that data set. And the reward function that you're trying to learn in inverse reinforcement learning plays the same role as the discriminator. So it's generally trying to say that the example demonstrations that you got, which is the same as your data set, have high reward, and things that your policy is trying to generate it has low reward. So just like in generative adversarial networks, you only get examples of positive data points.
Okay.
Of successful demonstrations.
Okay. It strikes me that there's, some signal in partial successes to some degree, and it makes me wonder what research is being done out there, in that direction, if anything.
Yeah, so actually one interesting thing is that humans, even if someone isn't successfully doing a task, humans can typically infer what they were trying to accomplish.
Right.
So that's actually one of the things that I'm working on right now is an algorithm which tries to learn from unsuccessful demonstrations that were still going in the right direction and still have enough signal to indicate what goal they were trying to achieve.
Okay, and so what's the approach there?
So the approach that we're trying right now is an approach based on few-shot learning or meta-learning. And I guess another term for meta-learning is learning how to learn.
Okay.
So,
and just if I can interject, I think you mentioned also one-shot learning previously. So we've got this, spectrum of learning, if you will. One shot is, learning on, one example. Few shots is learning on few examples. There's also no shot learning, which is learning on no examples. And then meta learning is orthogonal to the end shot issue, or is it not?
So few shot learning and one shot learning are typically achieved using meta learning algorithms.
Okay.
So meta learning is somewhat of a broader class of algorithms.
Right. Okay. So apologies, you were saying. I think you were saying that you were talking about how you're using meta learning or learning to learn to, solve this problem of learning from failed examples.
Yeah. So at a high level, what we're working on is being able to collecting a data set of examples of demonstrations for different tasks and corrupting some of those demonstrations with noise, and then trying to have a system that learns that the corrupted demonstrations, that learns basically how to do the correct thing from the corrupted demonstrations.
And so in this example, what is the demonstration? Are we still talking about the shape sorting cube, or is this something else? And then what is the noise? Are we talking about noise added to sensory input? Are we talking about noise in some representation or perturbations in some representation of, the underlying process? Or are we talking about, noise injected into some layer of the deep neural network? Or
By noise, I just mean noise injected onto the actions, so the output of the neural network of the demonstrations. So essentially the labels of the demonstrations.
Okay.
And that will make the demonstrations suboptimal.
Okay. So basically, you've got some label data that you're training a model on, and you just mess up some of the labels sometimes.
Essentially, although we're not training a model in the typical way. So in this work, we're building on some of my recent work on few-shot learning or one-shot learning.
Mm-hmm.
Few-shot learning is just kind of the general case where a few could be 1 to 10 or maybe a little bit more, where we try to learn a representation that's very quickly adaptable to many different tasks.
And maybe let's dig into the few-shot learning issue and talk a little bit about just, your approach, what you have done in your recent research, but also what others have done, and, a little bit of a background into the problem domain, if we could.
Yeah, absolutely. So in few-shot learning, the goal is to be able to do a new task from only a very small number of data points from that task. So an example of this is in the visual recognition realm is, say that you're given a picture of a Segway, and then your goal is, given that single picture of a Segway, be able to classify other examples of Segways successfully. And the way that you learn how to do this is get a data set of lots of different types of objects with a few types of each different object, and you learn about the variation across objects. So you actually learn how to identify objects just from one example.
And so is the data set that you're referring to, is that a labeled data set, or is that an unlabeled data set that you're just learning a bunch of things from?
Right now, it's a labeled data set.
Okay. And is it a labeled data set? What are the nature of the labels? Meaning, is it labeled with, objects, or meaning this is an orange, this is a cat, or is it, some kind of labels of the physical attributes of the things that are depicted?
It depends on what you want to do. If your goal is to do what's called one-shot image classification, then you take a standard image data set that has an image and its corresponding label and a full data set of that. Mm-hmm. And just like ImageNet, MNIST, there's a data set called Omniglot that's very popular for one-shot learning. And yeah, that's the nature of the data set that you use for meta learning.
And so you have, let's say, ImageNet. You have ImageNet, huge database of labeled images, and, we'll assume that there's no segues in ImageNet, and then you're basically trying to show it a picture of a Segway, and then you're showing it a labeled picture of a Segway, a single labeled picture of a Segway, and you want it to be able to identify subsequent Segways.
Yes.
Correct? And I guess the question what I'm wondering is, why do the labels in ImageNet matter? Like, why does it matter if, we have labels for oranges and these other things? I'm imagining that what's happening is you're throwing all that data, or you're training a deep neural network against all of that data. And then, within, the various layers of the neural net, it's kind of figuring out, textures and colors and geometries and curves and edges and things like that. And it's using that to identify, a Segway. Why does the fact that the data set is labeled matter in that case?
Yeah, so that's a very good question. So it actually doesn't matter that it labeled an orange as an orange or a banana as a banana. What matters is that it is labeled in the sense that it knows, like, this set of images is one type of object, this set of images is another type of object.
Yeah, that makes sense. Okay, so you're basically, the label is a way to communicate, clustering or similarity of like images, and it can use that to properly form the internal structure of your neural net to reflect all these things.
Yes.
Okay. Have you gotten yet the specifics of how folks are attacking few-shot learning based on, having, with ImageNet and things like that? Like, are there specific network architectures or specific training techniques or, things like that that lend themselves to building these few-shot models or meta-learning models?
Yeah, so there's actually a few fairly broad classes of techniques for solving this problem. One of the perhaps easier class of methods to explain is a class of methods that tries to learn an embedding of images such that when you run nearest neighbor or do like comparisons in that embedding space, you can very accurately generalize from just one or a few examples.
And just for background, an embedding is basically taking a set of images and mathematically kind of turning them into vectors that somehow relate one to the other. So say that again with that as background. You
learn an embedding space such that when you make comparisons in that embedding space, you can generalize well from just a single example.
So you're kind of learning an embedding that kind of maximizes the distance between your examples, basically.
Yeah, and then at meta test time or at test time, you're given 5 examples of, or one example of 5 different objects, so 5 images total. And then your goal is, well, put those images into your embedding function to get the embedding of each of them. And then you can just do, when you then get a new image, then you compare it to all of those, each of those 5 embeddings. And the closest one is then you assign the class of that example to the new image.
Okay. Yeah, I need to do a show just on embeddings and Word2Vec and all these things that I've been meaning to learn more about and haven't really had a chance to dig into yet. So you said there are a number of techniques, and that's one of them. Are there others that come to mind?
Yeah, I'll talk a bit about the approach that we developed for my most recent paper. So the method that we developed was largely inspired by fine-tuning. So in computer vision, if you want to get good results on whatever task that you're doing, typically you'll take a network that was trained on ImageNet, start from that network, start from the weights of that network, and then fine-tune it on the task that you care about.
AKA transfer learning, right?
Yeah, exactly. But if you try to do this directly for one-shot learning, where you only fine-tune it on one example, is going to overfit a lot. So it works well for transfer learning with a sufficiently large training set for the tasks that you care about. Where sufficiently large isn't as big as ImageNet, but it's of reasonable size. And so the approach that we take is to actually optimize for a set of features like ImageNet, such that when you fine-tune on a small number of examples, you get good performance, good generalization on that task.
Okay, and how does that work?
So you can write down this objective. It has a gradient in it that comes from the fine-tuning procedure. What the objective looks like is essentially you have your original weight vector, the features that you're trying to learn, and the updated feature vector, which is just the fine-tuned version of that. And you're trying to minimize the loss of that updated feature vector with respect to your original parameter vector.
I say but I think the limits of not being able to have a whiteboard in front of me have just, we've reached that point. But what I kind of heard in there was, if you think to linear regression, right, you are using these gradients to try to get you to some kind of optimum, and you are iterating over or descending, these gradients, thus gradient descent. And what I heard was you are kind of tweaking the way you are descending the gradient so as to do something. Is there a way to finish that sentence?
Yeah, so you're tweaking your loss function such that you're optimizing for the performance after a gradient descent update on that task. And you do this for a wide variety of tasks. So I guess the gist is to train for a parameter vector that can be very quickly adapted for a wide variety of tasks. And we can do this with gradient-based methods, essentially just with SGD.
Okay. So you're basically changing your loss function so that, it's kind of like a technique like dropout and some of these other things where you're doing, funky things to your loss function to be more impervious to overfitting.
Kind of. We're actually optimizing.
At the that kind of was like at the 300 million thousand foot, level. Yeah.
You can kind of see it as optimizing for good generalization.
Right.
And one of the nice things about this approach is that, well, it sounds kind of complicated, but when you actually write it down, it's incredibly simple. I implemented it in less than a day, and you could apply it to few-shot classification like I talked about before and get really good results, but you can also apply it to a wide range of other few-shot learning problems, including few-shot learning of behavior.
Okay. So I think I'm just going to take this as a challenge to myself and anyone else who's listening that wants to dig into this to actually get your paper and go through it. And, perhaps we'll reconvene after I've done that and see if I am able to have a coherent conversation about what we're discussing here. And so in order to facilitate that, what is the name of the paper that you're describing?
Yeah, it's called Model-Agnostic Meta-Learning.
Okay.
Yeah, those are the first 4 words of the title.
Okay, well, we'll find that paper and we'll make sure that the link is in the show notes. And anyone else who wants to, dig into this with me, can just drop a comment in the show notes and we'll kind of exchange notes as we learn this together.
Yeah. I'm also thinking about writing a blog post on it at some point in the near future.
Oh, really? Awesome. Well, if you do that, I would, be happy to, help in any way, review it or ask you more dumb questions or whatever.
Okay, great.
And so since we're talking about some of your research and your papers, any other pointers to papers that, folks can dig into based on the things that we've talked about? What are the top 3, papers that you'd want folks to take a look at to get a sense for your work?
So the first one would be the one that I just mentioned. The second would be a paper on inverse reinforcement learning called Guided Cost Learning.
Okay.
The third, let's see. It depends on how much reading they want to do. I think that I'll refer them to the paper that starts with Deep Visual Foresight.
Okay. That sounds compelling.
So that one we didn't talk about that much, but essentially that one's trying to learn a predictive model of video, being able to predict the future video given the actions that the robot's going to take.
Okay. Awesome. Well, we'll have links to all of those in the show notes. Before we go, I got a request from one of our listeners a while ago, Shreyas, who was about to embark on his own PhD pursuits. And he asked if we could get a PhD student on and talk about a little bit about their experiences as a PhD student and, what are some things to keep in mind to, be successful in pursuing research in this field. And I was wondering if you would maybe share some of your thoughts. You are obviously, doing amazing research. You've got 2 great advisors. Like, what are your secrets to success?
Yeah, I think that it's important to continuously develop and learn throughout your PhD. So reading a lot of papers, especially these days with arXiv having a tremendous number of relevant machine learning papers every day, and working on research skills, learning from others around you. So at the beginning of my PhD, I started working with a postdoc very closely, and I learned a lot from him on my first project. And the ability to, at the beginning, learn from people who are more senior from you is very helpful, because there's no one perfect way to do research. I mean, if you're trying to solve problems that people haven't solved before, and that's hard, and the way to approach that is different for everyone, but I think that there's a lot to be learned from people who have been at it for a few years or more. So I think that learning from others and being open to that is very important. I've also developed my writing skills a lot in graduate school. Depending on where you want to go, that can be very important, especially if you want to go into academia or if you want to continue publishing. Let's see. And then I think that work ethic is important. Trying to keep up with the field these days and trying to actually get things to work takes a lot of work. By nature, research is trying to tackle unsolved problems. And if those problems were easy to solve, then they wouldn't be unsolved problems.
Right. So in other words, no shortcuts.
Yeah.
How do you keep up with arXiv and your paper reading list?
I don't think I necessarily have a good solution, but typically what I do is check arXiv every day or every other day and see if there's any relevant papers. I will read papers to a varying degree based on how relevant it seems and how good the paper seems. And I also don't worry too much about missing papers, because if it is a really good paper, then it will rise up through conferences, through publications. I'll see them at different publication venues, or they'll become popular or common knowledge.
Right. And so is it a worthwhile question to ask, like, how many papers do you read, day, week, month, or what have you? Or
yeah, I read a paper end to end very infrequently. I guess the papers that I have to review for conferences, I will read end to end, and I will only read other papers end to end if they are very relevant, or if I volunteered to present it at a group meeting. We have reading group meetings fairly regularly, so that's another good way to keep up with a lot of new papers, is find a group and have someone volunteer to present a paper or kind of present the key findings from a paper in that group. So that not everyone has to read everyone. Someone can just read it and then summarize the points that are relevant to that group.
And is there, for papers that are directly relevant to your research, is there a level beyond reading end to end where, you're actually kind of digging into the math and trying to figure out, what were some maybe missing steps that were glossed over in the paper, or you're implementing them or things like that? Or do you do that, fairly infrequently as well?
Yeah. So if a paper is along the lines of what I'm working on, then typically I'll want to compare to that paper or compare to some version of that paper. And so that will involve grabbing an open source implementation or emailing the author or re-implementing it myself. And yeah, also thinking about the shortcomings of the paper is important. So one example is that I'm currently working on a certain application of meta learning, and there was a new paper that came out on a very similar topic. And one of the shortcomings was that the data set required for meta learning was huge. And so one of the benefits of meta learning is that at test time, you can learn from a very small amount of data. But if you need a ton of data to learn that few shot learner, then it's not going to be feasible for applying to real robotic systems. And so that shortcoming is something that I'm, one, aware of when I'm working on this problem, and two, something that I want to address concretely in the work that I do.
Got it. I'm wondering out loud now, but I am intrigued by the thought of doing like a virtual paper reading group, like something along the lines of a podcast or an extension of the podcast. And I wonder if there are any readers out, or listeners rather, that would, I guess, also be readers, would be interested in something like that. So if you are, shout out in the comments or Twitter or something like that, and people are interested, maybe we can find a way to do something. But I guess with that, Chelsea, you have been very gracious with your time, and I really appreciate you jumping on the Skype line here. It's been a really interesting conversation, and I have definitely learned a ton, and my brain exploded a little bit, which is also a good sign. Thank you. Thanks so much.
Yeah, happy.
Awesome. All right, bye-bye.
Yeah, bye.
All right, everyone, that's our show for today. Thanks so much for listening and for your continued support, comments, and feedback. We really, really appreciate hearing from you, and we love to incorporate your ideas into the show. I'd also like to thank our sponsor, Bonsai, once again. Be sure to check out what they're up to at bons.ai. And one last reminder, next week, I'm at the O'Reilly AI Conference in New York City. You can still register using our discount code PCTWIML, PCTWIML, for 20% off. And if you live in New York or will be at the event, let's plan to meet up. I'm partnering with the NYAI Meetup to host a happy hour on Thursday evening after the event. If you'd like more details, please sign up using the form at twimlai.com/nymeetup, and we'll keep you posted. The notes for this episode can be found at twimlai.com/talk/29. For more information on industrial AI, my report on the topic, or the Industrial AI podcast series, visit twimlai.com/industrialai. As always, remember to post your favorite quote or takeaway from this episode, and we'll send you a laptop sticker. You can post them as comments to the show notes page, via Twitter at twimlai, or via our Facebook page. Thanks again for listening, and catch you next time.